Everyone, I hope you're doing well. Today we're going to go into lesson 3, which is going to have 2 parts. I'm going to upload 2 different videos for it. And so let's go ahead and jump into lesson 3, part 1.
So welcome back. Here we have the same setup as the last time. I have my switch and I have bulb. I've now labeled bulb A, so we can have a clear conversation about what's happening in our setup, because in addition to bulb A, I've added bulbs B and C, and we're going to look at how these bulbs interact with each other when experiencing a potential difference from the battery. So to start, I'm going to go ahead and flip my switch. And here, when I flip it, we see with this closed circuit that bulb A is illuminating at the same brightness as it was in the previous demonstration. Well, if it's illuminated at the same brightness as the previous demonstration, knowing that power is equal to current times voltage, and knowing that the voltage source has stayed the same, we can infer that only bulb A is in this circuit. And sure enough, if we follow the path through here, up to here, to here, through the brass sheathing, going down to the bottom of the bulb, through this copper to here, recall why I can't go this way, through the copper, right? Now we have 2 options. We can go up to bulb B, or we can go over here to the right. And just to be clear, that's not really touching each other. Let me adjust that a little bit. Okay, so I can go up through bulb B, or I can go over here and down to here. Well, if I go over here down to here, I can go to this horizontal piece connecting these 2 ends here that we discussed in the last lesson. Then we can go up here to here. I can go up through bulb C, or I can go this way back to the negative. So we can see the high and the low potential are connected to bulb A, so therefore bulb A illuminates. That can also help us explain why B and C do not light up. Well, if we go from the high over, up, well, the brass side here, remember it goes through the bottom, through the filament into the brass, is not connected to my low potential here, so it will not illuminate. I need to have both the high and the low. Remember that potential difference is what allows the charges to move. With C, we have the same problem, right? We have the problem that the low potential side is not connected. I do have my high potential, right? I have it coming through here, down, connected over to this point, but I have nothing that's connecting to this short terminal of the battery. So only A is connected. But what I'm going to do now is I'm going to rearrange this, and I'm going to set it up so that B is connected to the circuit. To do that, I'm going to remove this here. Everyone, just look at A quickly. I want you to remember the brightness of A. It's pretty bright, right? You can barely actually see that letter A. Take this thing here, and I'm going to move it. I'm going to place it right here. What happened to the bulb A? It got dimmer, didn't it? That got dimmer, and B started to light up. So now I have both A and B illuminated in my circuit together, and A has decreased. Well, recall from the potentiometer, as I decreased my potential difference, my bulb brightness decreased, and we said that that meant that the current decreased in addition to the potential difference decreasing. Well, now my brightness decreased, which means that the current through A must have decreased, and the potential difference across A must have decreased. Well, now let's get C involved, right? So what I'm going to do now is take this thing here. Ready, watch again. It's going to go from there. I'm going to move it, and I'm just going to take it here. I'm going to take it from this brass portion to this portion. Now A, B, and C are all illuminated, and they're all lit up just as bright as the other, and A has decreased in brightness, which means that current must have decreased yet again. So, watch, A dim, A slightly brighter, A even brighter. And so this raises the question, which will be our aim. Why does bulb A get dimmer when I add bulbs B and C to the circuit? Now let's go ahead and start answering that question. So the type of circuit we're discussing right now is what's called a series circuit. A series circuit is a circuit that has all elements connected to each other without any sort of branching. So they kind of make a continuous path. Okay, now that word series, when it comes to circuits, more generally means elements that are connected without branching. Okay, so elements that are connected without branching. And what I'm going to do now is I'm going to just use a second piece of paper to draw the circuit, and then we'll come up with the rules for a series circuit underneath our notes here. So this circuit will consist of a battery, like this. The battery will go up and over to a ammeter that I'll label A1. That's connected to resistor R1. That'll go over and down to an ammeter, a little small there, A2. That's connected to a second resistor, of course R2. That's going to go down and over to a third ammeter, A3. That's connected to my resistor here, and then up to my battery, and this would be R3. Okay, so that is my series circuit. Well, let's think about that demonstration, and I want to talk about what each of these ammeters will read, or what the current is in a series circuit. Well, each bulb acted as a resistor for our purposes. Now, of course, a bulb is a non-ohmic resistor, and these are resistors, but since the potential difference is the same, we don't have to worry about a change in resistance because the bulbs remain at the same brightness the whole time. So, well, this bulb was as bright as this bulb, which was as bright as this bulb, and they're the same type of resistors, and we said that brightness pretty much corresponds with the current through the circuit, which allows us to say that the current through this equals the current through this equals the current through this, or I1 equals I2 equals I3, which must also be equal to the total current that's coming out of the battery. And so we can see that for the current, the total current in a series circuit is equal to I1, which is equal to I2, which is equal to I3. Worded a little differently, the current in a series circuit is the same at all positions of the circuit. Okay? So A2 will read the same as A3. Now that may seem strange, right? Because A2 is before this resistor. So shouldn't that move faster than this one slower? Or, I mean, you can also reason the other way. But the truth is no, because for every electron out of the battery, and now I'm going to go with electron current, not conventional current, for every electron out of this little one, one comes in, which means everyone that goes in this resistor comes out, everyone that goes in this ammeter comes out. And in this resistor, out, in this ammeter, out. And so you end up having the same motion of electrons throughout this entire circuit. Now, the next thing we want to look at for this series circuit is what we call the equivalent, or we can say the total, or the effective resistance of the circuit. And all three of these words will mean the same thing to us. It's just kind of measuring how all of these resistors interact in this circuit to help determine the total current, assuming that we know some, I'm going to say Vs, potential difference of the source. Okay, well, let's see. When we had one bulb, it was very bright. When I had two bulbs, this bulb became dimmer, which meant the current decreased. When I added a third bulb, this bulb became even dimmer, which means the resistance increased even more. How do we know the resistance increased even more? Because the brightness dropped, which means the overall current decreased. The source voltage, Vs, stayed the same. Ohm's law tells us that V equals IR. And so if V stays the same and I decreases, R has to increase. That gets us to our equation here, which is that the total resistance, or the Req, is equal to R1 plus R2 plus R3, ... Because if I added a fourth resistor, we'd just say plus R4. that's the equation for my equivalent resistance of a series circuit. And hopefully that demonstration with the bulbs made the reason for that equation clear. All right, so we've done current, we've done resistance. Hopefully we can see that the next thing we're going to look at is the potential difference of this kind of circuit. How does the potential difference across each of these resistors relate to each other? To discuss that, we're going to want to take some voltmeters, and we're going to want to read, where did I get that from? The potential difference across each resistor. Uh-oh, I'm running out of space here. Could do this. Okay, so you can see we're taking our voltmeter and we're putting it here, here, and here, and we're going to compare that to whatever this reads here. To answer this, I want to start with an equation, and that equation is going to be delta V source, the potential difference read by that voltmeter here around the battery, which is just the potential difference of the battery, equals the total current in the circuit times the equivalent resistance of the circuit. Now, this is really just a restatement of Ohm's law, isn't it? But this is kind of like for the system of the circuit. Much like how when we dealt with forces, we can look at the force on individual objects, that's this right here, or we can look at the force on the total system, that's kind of like this right here. Okay, so this potential difference of the source is the total current, this right here, times the equivalent resistance of my entire circuit. Well, I can rewrite this as I total times, well, what is Req? It's this right here, isn't it? R1 plus R2 plus R3. I also know that I total is equal to I1, which is equal to I2, which is equal to I3. So if I want, I can rewrite this as I1 R1 plus I2 R2 plus I3 R3. Well, what is I1 R1? That's Ohm's law. That's V1, isn't it? So that's going to be equal to, and I'm going to throw the deltas in now. It doesn't matter again. When I use V in circuits, I'm really talking about the potential difference, plus delta V2 plus delta V3. In other words, the voltage of this voltmeter plus what's read by this voltmeter plus what's read by this voltmeter is equal to what's read by this voltmeter. Okay? And those are our three equations for a series circuit. Okay? Great. Now, I like to make a gravitational analogy to electrical circuits. And so what that looks like is what I have here. Now, this is the gravitational analogy for a series circuit. I have, again, my water here with a pump that's pumping up through this pipe up a potential difference of delta Vs. That potential difference is like the potential energy gained by the water as it goes up and up and up and up. It's brought to the top of this hill, and then it drops down this bit and then flat, and then this bit and then flat, and then this bit and then flat. Well, when water runs down a hill, we say that it's a current, it's a river, right? It's flowing. Each of these little drops I'm going to define as being R1 or R2 and R3. Now, I know the analogy doesn't hold perfectly because zero resistance would be more like going down is a lower resistance, so it's not perfect, but I think it gets the point across. The battery or the pump lifts up the potential energy. As it goes down each resistor, it drops, and then it drops, and then it drops, eventually ending at the same potential, eventually ending at that low potential, right? After the battery picks it up to the high potential, right? So we can see that the total potential energy gained by the pump or the battery is equal to the sum of the potential difference lost by each element in the circuit. What we can also see here is when a river flows, right? If we build up a little dam here, that's going to back up the flow of the river, right? It's going to slow down the river. Well, when I do that, the water up here is going to move a little slower because it can't get past this, and then it's going to get over the dam slower, so the water down here is going to move a little slower. And the water at each point in this river will flow at the same rate after it equalizes with some time. So the total current is just the the same in all positions, and I should not have plus signs here, excuse me, I should have equal signs. So the current is equal at every part in the river. Now, let's move on to an example. Let's say we have this circuit here. And I'll move this out of the way so we can look at our equations. Okay, those are our equations for a series circuit. If I have a battery here that is connected to a resistor here that goes down to here, and I have it put an ammeter right here that's connected directly to this resistor here and then connects back to the battery. Well, if we just look at the basics, a high potential plate is connected to a low potential plate, so the current will flow through the resistor from one side to the other, conventional current versus electron current. This I'll name R1 and this I'll name R2. I'm going to take some voltmeters and connect them up. V1 will be across R1. V2 will be across R2. And then we're going to know some information in this problem. What's provided to us is R1, which is equal to 10 ohms, R2, which is equal to 20 ohms, and the total current, which is measured by this ammeter here, is going to be 4 amps. So that's the information I know. Now, typically speaking in a problem, I would be asking you to solve for a specific thing. But I think for us, what's more useful is solving for everything, because if you can solve for everything in the circuit, you're in pretty good shape. To do that, we're going to set up what's called a verb table. Well, this is a table of potential difference, current, resistance, and power, and whatever element we're referring to. So I'll draw this across like that. Then I have 1, 2, 3, down like this. Okay. And where I have element, I'm just going to put it. I have resistor 1, I have resistor 2, and then I have the total or equivalent or whatever word I choose to use. What information do I know? Well, I know R1 and R2, right? So R1 here, I'll put 10 ohms. R2, I'll put 20 ohms. I know that in a series circuit, the equivalent resistance is the sum of the resistors. So R1 plus R2, well, that's going to be 30, isn't it? Because that's just 10 ohms plus 20 ohms. Okay. Then what else do I know? I know the total current is 4 amps. Oh, sorry, wrong thing there. 4 amps. But I also know that I total is equal to I1, which is equal to I2. And that is 4 amps, which means each of these is 4 amps. Next, I can just use Ohm's law here. V1 is equal to I1 R1. I1 R1, 4 amps times 10 ohms, or 40 volts. Same thing here, 4 times 20, right? Well, what is that going to give me? That's going to give me 80 volts. Here, 4 times 30, what is that? That's 120 volts. And notice, this is my system, right? The system should be the sum of the individuals. 40 plus 80 gives us 120. It works. Then, power. Power is equal to IV, or VI, whatever, either way. What is that? That's 4 amps times 40 volts, or 160 watts. Apply the same logic here. This times this gives me 320 watts. This times this gives me 480 watts. I want to check my work. Well, the system should be the sum of the individuals. 160 plus 320 gives me 480. And there we go. We have it. It works. Okay? So there is my completed verb table for a series circuit example. Now, what I want to do is quickly jump back to my demonstration. All right, so here I have my setup. Okay, positioned in front of you. Now, I'm going to flip my switch. Hopefully it works. Nope, I have some loose connections here clearly. Get it back together. Okay, so I have my 3 bulbs illuminated, A, B, and C. Now, following the current out of the high potential through the wire to the switch, around to here, high potential still here, through that casing, through the filament, down through the copper, over to here, up through the copper, through the bottom, through the filament, through the side, over, who's in it there? Over, through the side, up through the filament, down through the bottom, through the copper, over to the negative. So we see we have a complete closed circuit because the battery is connected high to low potential. What I'm going to do next is I'm going to take this wire here. Hopefully this wire's long enough. It may not be. I'm going to take this wire here and I'm going to connect it from this point to this point. All right? I want you to watch what happens. Okay, so bulb C is no longer in the picture. Now I'm going to take it and I'm going to go from this point to this point. Ready, watch it. Yeah, slipping out on me. Let me get a different wire. This one's a little bit not quite good enough. Okay, I'm going to take this wire and I'm going to go from here to here. Okay, so when I do that, you notice that A got brighter and so did C. Ready, let me remove again. Hopefully this is worth it, right? Suddenly I have a dimmer circuit, right? Oh, dimmer circuit, they're just off. Okay, so A and C are dim. Oh, come on. A and C are dim. Right? I take a wire, I'm going to use a longer one right now because it'll work even better. And I'm going to put it right here. Okay. Then when I put it from there to there, what happens? Well, A and C become brighter, which means that the current through A and the current through C must be greater than it was before. It also means the potential difference across A and the potential difference across C is bigger than it was before. And we can explain that because V equals IR, the resistance of the bulb has stayed the same, assuming that it's non-ohmic, which is what we're working with right now. Well, if it's non-ohmic and V equals IR, R stayed the same, and I increased, V must also increase. But why did that happen? Why did B suddenly seem to disappear? It no longer affects the circuit at all, but A and C are brighter. Well, let's follow the current, right? Out of the high potential, through the switch, up through here, through my bulb, down through the copper to here, to here. Oh, now I have a few options, right? I can go through the portion here and then up through this bulb, which is a resistor, or I can take this nice copper path, a low resistance path, and go straight to C. Well, if I'm an electron, I'm going to end up taking this nice low resistance path and not going through this bulb. And so what ends up happening is the current bypasses bulb B and goes straight to bulb C, down and then out to the low potential. This you've heard of before. This is what's called an electrical short circuit, or a short circuit. And this is when we provide a low resistance path okay, so current can bypass an element in your circuit. Okay, so it allows to bypass an element. If we look at this in a circuit diagram, I can have my battery here that goes up to here to a bulb, let's say, that goes down and over to a resistor, and then back to the battery. Well, if I have this running, I have some sort of an I total, which we know is equal to I1, name that 1 and 2, which is equal to I2. And then I can say I total is equal to Vs over Req. Right? That's kind of like my system equation. Well, if suddenly I take a wire and I create an alternative route, my current can come up here, over here, through my bulb, up through here, down through here, and now it's going to say, no, I don't want to go through that resistor. I'm going to go this way and back to my battery. As a result, the equivalent resistance of the circuit decreases. This stays constant, right? I didn't change my battery, so my current increases. My total current increases, which means that this current increases. If that current increases, my bulb gets brighter. And that's exactly what we just observed in the demonstration, where I connected that wire across bulb B, making it go dim and brightening bulbs A and C. So I hope you found this lesson useful, and stay tuned for lesson 3.2, where we'll be discussing a arrangement of these same 3 bulbs, but in a way that results in a very different outcome.